Well, Born-Haber cycle was invented by two German physical chemists, Max Born and Fritz Haber. And this cycle was used for the first time in 1919 to determine the lattice enthalpy of an ionic compound. So what exactly is lattice enthalpy? Let's say I have 1 mole of ionic compound, solid sodium chloride, decomposes to 1 mole of unipositive sodium ions and 1 mole of uninegative chloride ions. So the enthalpy change that takes place when 1 mole of an ionic compound is dissociated or decomposed into its corresponding ions separated by an infinite distance, and that enthalpy change that takes place during that process is called lattice enthalpy. And this is difficult to measure directly. Why is that? Because as soon as they dissociate, the compound dissociates, these ions form ionic pairs like that. So they're not truly separated at an infinite distance. They come together to form ionic pairs. So it is difficult to measure this lattice enthalpy directly. So Max Born and Fritz Haber, they came up with an indirect method. They said, well, you can use the Hess's law to determine enthalpy or lattice enthalpy change indirectly, which should be pretty much equal to the direct method. So they used an indirect method using the enthalpy of formation. So let's say I have, so the equation for enthalpy of formation for sodium chloride would be the enthalpy change that takes place when 1 mole of pure sodium chloride is formed from its elements under standard conditions. So this is the enthalpy of formation, which equals to negative 411 kilojoule per mole. Right? That is the standard enthalpy of formation of sodium chloride. And they said, well, this standard enthalpy of formation, this whole thing doesn't happen in one step, but the value that we got here is a sum of the enthalpy changes that are happening in smaller steps. So I'm going to discuss this enthalpy change of formation or standard enthalpy of formation of sodium chloride in 5 different steps. So the sum of the 5 different steps enthalpy changes should basically be equal to the standard enthalpy of formation. So in step 1, so solid sodium is basically sublimed, undergoes sublimation to form gaseous sodium atoms. So we call this as the enthalpy change corresponding to this sublimation process. They also call this as atomization. So delta H atomization theta, that equals to positive 108 kilojoule per mole. So that's an endothermic process. You're trying to separate the closely packed sodium atoms into loosely bound and spread apart gaseous atoms. So that's endothermic. So that's the sublimation, also known as atomization, and the enthalpy change corresponding to that would be delta H atomization, which is positive 108. Step 2, similarly, the half chlorine molecule that we have, which is in gaseous state under standard condition, it also dissociates to form free chlorine atoms. So that's, again, we can call that as delta H atomization. The process is simply dissociation. You're dissociating or splitting up a molecule into free atoms. So we can call that as delta H atomization. So that would be positive 122 kilojoule per mole. So this is nothing but half of the average bond enthalpy of Cl2 molecule, which you can get it from your data booklet. So in step 3, so whatever the sodium gaseous atoms that are formed in step 1, so we have 1 mole of sodium gaseous atoms. and they're transformed into gaseous cations, 1 mole of gaseous cations. So we're trying to remove 1 mole of outermost electrons or valence electrons from 1 mole of neutral sodium atoms in gaseous state to form 1 mole of unipositive sodium ions in gaseous state. So that would be nothing but ionization energy, delta HIE. That is the first ionization energy of sodium. And ionization energy is usually endothermic process because you need to remove the electrons from the outermost shell. So that is about 494 kilojoule per mole. That's 494. Similarly, the chlorine gaseous atoms that are formed in step 2, they gain, if I have 1 mole of chlorine gaseous atoms, right, whatever the 1 mole of electrons that are lost here by sodium, they're gained by this neutral chlorine atoms. So steps 3 and 4 are basically transfer of electrons. Sodium being a metal loses and chlorine being a non-metal gains electrons. So chlorine forms a chloride ion. So if I start with 1 mole of chlorine gaseous atoms, I end up with 1 mole of uni-negative chloride ions. And the enthalpy change that corresponds to this is, it's called electron affinity. So electron affinity is an exothermic process. So this much of heat energy is lost to the surroundings when chlorine atoms gain 1 mole of electrons to form 1 mole of uni-negative chloride ions. So that's again kilojoule per mole. And finally, so the sodium unipositive ions and the chloride ions basically combine. So Na plus gaseous from step 3 and Cl minus gaseous from step 4 combine to form sodium chloride, 1 mole of sodium chloride, which is a solid. So this is nothing but, if you compare this step to our very initial step, this is the reverse of our lattice enthalpy step here. So I can write this as the reverse of lattice enthalpy, delta H lattice. Because this equation number 5 is nothing but the very first equation that has been flipped or reversed. I just want you all to take note of that. So what I want to try to say here is our goal is to calculate delta HF first before we calculate lattice enthalpy. So as I said, the standard enthalpy of formation is basically equal to the sum of all these enthalpy changes from steps 1 through 5. So I can say this equals to delta H, or let me say it's the sum of step 1 plus step 2 plus step 3 plus step 4 plus step 5 enthalpy changes from all these steps. So if I add up all the enthalpy changes from steps 1, 2, 3, 4 and 5, that should be equal to delta H. In other words, this should be equal to delta H atomization of sodium plus delta H atomization of half Cl2 plus delta H IE, that is the ionization energy of sodium, plus delta H theta of electron affinity of chlorine, plus from step 5 we have lattice enthalpy. So this would be equal to plus negative delta H lattice, right? So we know delta HF theta equals to negative 411 from the one of those first steps, 411 kilojoules per mole. And we know delta H atomization of sodium is positive 108 kilojoule per mole, plus delta H atomization of chlorine is 122 kilojoule per mole, and delta H ionization energy of sodium is about 494 kilojoule per mole, plus the delta H of electron affinity of chlorine is negative 364 kilojoules, plus of minus, that would be minus delta H lattice, let's say lattice. So we know all these values, so we can use these values to determine delta H. So that would be equal to, let's say the sum of these would be negative 411 kilojoules per mole should be equal to, so the sum of all these values should be about positive 360, and we have a remaining term which is delta H lattice, or negative delta H lattice equals to negative 771 kilojoule per mole, negative 771 kilojoule per mole. Or, so in other words, I can rewrite this as delta H lattice should be equal to positive 771 kilojoule per mole. So that's what basically how we can determine delta H lattice indirectly using the sum of the enthalpy changes that happen during the formation of sodium chloride.